You look at it when I record, right? I'll just put the chat up. Okay. That's weird, not having, I'm so used to having people online. Is this working? Okay. Oh. Okay, it is working. Okay. Okay, I'm so used to having people online. It's like weird. It's weird being face to face. It's weird having people online. Or not having people online as well. I don't know. Maybe I'm weird. Maybe I'm the one that's weird and the world's normal. But anyways, anybody have any questions about anything before we start? Had a question about when things are due, and I originally said tonight at midnight, but it doesn't, to be truth be told, it doesn't matter. If you don't do it, I'm gonna bug you. But I mean, I basically accept any excuse. I need to caution you against cramming chemistry because it doesn't work. Like some subjects you can cram. I mean, some things you need to have sink in a little bit. Like for me, like languages, like whenever I hear this stuff on like the radio or like, oh, you can learn a language in like 6 weeks. Like there's no way. There's no way I could learn a language in 6 weeks. So, although I must admit, when I was younger, I learned Spanish pretty quickly, but that's because I was immersed in Spain. But anyways, that's more of a youth and survival. I guess you guys are young enough, you might be able to do that. But anyways, we are talking about kinetics. And I said, in my opinion, this is the hardest chapter of the entire book and entire 161, 162 series. And the reason is because it's calculus based. And you don't need to know calculus to do this class, although I'm gonna start class up by showing you a calculus proof. But I wanted to show you this proof just, I mean, because I'm also thinking beyond this class. You're not gonna be tested on calculus, you're not gonna be tested on this proof, but just so you know where you see where some of these equations come from. And so we're gonna talk about the integrated rate laws. And so how do we get the integrated rate laws? We take the rate laws and we integrate them using calculus. So the rate is equal to a rate constant times concentration of A. That's the first order rate law expression. And A is a reactant, so it's negative, it's disappearing, and the rate law is the disappearance of A over the change in time. So A is going away, and we can rearrange this. Instead of capital delta, we can do incremental deltas or D's, and then we can rearrange such that we just multiply this one here. If you divide A and multiply dt, if you do that, you get this expression here. And then you can integrate. So again, if you haven't done calculus, that's okay. You can integrate from time 0 to some time t. And then, this textbook and many textbooks for initial, they put A0 is for initial. Sometimes it's I for initial. Sometimes, and especially if you speak British English, it's not, it's A naught, all for naught, all for nothing, all for zero. So 0, so some initial concentration to some final concentration at some time t. And the integral of dt is t. The integral of, integral of 1 over x dx, if you remember, if you've ever had calculus, it's the natural log of the absolute value of x. And x in our case is a concentration. So can anyone tell me what a negative concentration looks like? There is no such thing as a negative concentration. So it's just the natural log of the concentration. Limits for both. So for KT, it's 0 to T. For natural log of the concentration, it's initial concentration to some final concentration. So then you apply the limits. Minus KT is natural log of final temperature, concentration minus the natural log of the initial concentration. And then we can rearrange this in a few ways. Sometimes, so this equation, you can see it as minus KT is equal to natural log of a T over a 0. You can write it that way. You can write it as KT equals ln of initial over final, because the negative sign causes the fraction to flip. But also very commonly, you can see it written this way. And the textbook uses this one, and it's also classical, the way that they would write it this way: the natural log of some concentration sometime equals minus K, the K is the rate constant, times T, the time, plus the natural log of the initial concentration. And why would we write it that way? Because that's the equation of a line. So if you remember the y equals mx plus b. So, and this is one of the old ways of doing it, is do it graphically. I'm not going to require you to know how to do it graphically. We used to do a lab, or at least I used to do a lab. I don't know if I guess we're following Manoa for this semester, at least the online lab. I don't know what Dr. Fisher is doing for the other ones, but I don't think Manoa goes over an experiment like that. I did an experiment like this where we did the graphical stuff, but I'm not sure. I don't think they're going to do that, but it's one of those, I guess that's the way I was kind of taught chemistry and like equations of lines. So you calculus folks, have you studied integration yet, or you haven't gotten there, or you have that? So that looks familiar to you. So, but for me, I mean, I don't know if I can be as dramatic. My wife tells me I'm dramatic sometimes, but so for me, when I see these equations, like the ones I written in blue, and then the one I circled or whatever squared, I think this is really cool. Like, I mean, to me, like, so the fact that, this is a first order. This is, I've been watching the Star Wars too, from the book of Boba Fett, the first order. But I mean, this is a first order reaction, and you can rearrange it mathematically. So it's this integral, and the solution to that integral is the natural log. And what I think is really, really cool is, first of all, the mathematics. I mean, one of those like things you look at math, and math kind of predicts the way the universe works. It's really strange because almost everything is first order kinetics. I mean, I mentioned nuclear decay, banking interest, and almost all chemical reactions. In fact, you can force chemical reactions to behave in a first order fashion. And it all has to come down, among other things, to probability. So it's simple probability, and this relationship here, that inverse x dx integral is the natural log. This like describes almost everything in the universe. I mean, not like everything, but I mean like a lot of things that we can predict now, and we predict them very well. Money flow is very easy to predict. Nuclear decay, and overall, over long periods of time, it works perfectly. Of course, for instantaneously, it doesn't work very well, but well, it works pretty well. But I mean, you can get deviations, but long period of times it fits exactly. And same thing with chemical reactions. So, I mean, I think this is awesome. This is awesome that we have a mathematical expression that can predict things so well. And I mean, it's like, can you imagine a world that we didn't understand this? I mean, like if we're going around, before the age of reason, before like the 1850s, I mean, chemical reactions has happened. I mean, we thought they were from the gods, or even, well, I guess post-Christianity, it was the angels or something like that. We didn't understand anything. I mean, you see lots of things in literature and in society that suggests, like we have no idea what the heck's going on, and now we're like, okay, we understand things better. Of course, people still have faith and believe in deities, but I mean, it's kind of a different sense. It's not, not like, okay, I better do this, otherwise, my stuff's not going to work. So, but I think that's cool. So, but here is an example showing the graphical nature. So we have this chemical reaction, the decomposition of SO2Cl2. And if you have concentration versus time data, and if you graph it out, if you graph out the natural log of the concentration versus time, you get a straight line. And the slope of that line is the opposite, the negative of the rate constant. So, and it's especially now with computers, it's really easy to do. So I told you the way I was taught. I remember when I took general chemistry, I knew about I took calculus in high school, so I kind of understood all this stuff. And then when I got to college and I was studying this, I'm like, okay, this makes sense. It's all just, simple calc. And I'm like, the teacher wouldn't make us graph things out by hand. This is the 1990s. We don't, we're beyond that, right? So, but so, and I remember during the chemistry final, my teacher actually he gave us some data. I'm like, all right, tell me the reaction order, the rate constant, and that kind of stuff. Like, So then we actually, and he gave us graph paper, and then I remember I had to go and do that. And besides that, I'm just like, we could just use Excel, because I haven't actually made a graph, I think, in like a proper graph that I've gotten information from in probably 30 years. No, it wouldn't be 30 years, more like 20. So I've always had computers to help me. Don't worry, I'm not going to do that. I'm not going to make you do a graph by hand. And did you guys do that in high school and grade school? Did you ever have to make graphs by hand and then calculate stuff out? Okay, good. I'm glad you guys did that. So, but so the first order integrated rate law, natural log, and I'm dropping the concentration sign, minus KT plus natural log of A0. So it tells you a few things when you have a line. When you have your equation on a line, the slope is the opposite of the rate constant, and the y-intercept. So that y-intercept is the natural log of the initial concentration. So if you're given data, of course, like this, you can figure out some interesting things. So like what the initial concentration is for one. And why do I care about the initial concentration? So things like with nuclear decay, if you want to know how much stuff we had at the beginning. So they do that for determining the age of the Earth. So we know the age of the Earth is 4.6 billion years thereabouts. And we determined that by looking at the nuclear decay of uranium-238 and potassium-40. And both of those indicate that the initial start of it was around 4.6 billion years ago. So the idea was that's when the Earth formed, and then everything else decayed there. I guess it could also be that's 4.6 billion years after the supernova that formed the material for the Earth. That's the other way you could maybe look at it. I don't know how long it takes planets to form. I'll have to ask my wife that. Well, she's also not into planet formation, so my wife's an astronomer. So, okay, so let's do this the problem. So the decomposition of SO2Cl2 is first order, has a rate constant of 2.9 times 10 to the minus 4 inverse seconds. If the reaction is carried out at the same temperature and the initial concentration is 0.0225 molar, what will be the SO2Cl2 concentration after 865 seconds? So this, and students love this because, I mean, you remember last class? Did you guys feel like, how did you guys do? Are you okay leaving the class, or did you feel like, oh gosh, what did I get myself into? You're not reacting. But yeah, you're fine. Oh, good. Because a lot of times students are like, oh, good, awesome. I'm glad you guys are doing well. You did really well with the Clausius-Clapeyron equation too. So that'd be awesome. So we can have lots of A's in this class. But actually, truth be told, my 162 classes tend to have a very high pass rate, and they also actually, well, last year I had like 60% A's, which is wonderful. I mean, it's usually not that high, but hopefully maybe we can get 100% A's. There's 10 of you students in your class. It'd be nice to, I could say I have 100% A's. So anyways, so we have the first order integrated rate law. You just put in the numbers. So natural log of some concentration at some time, so minus KT. So rate constant minus 2.9 times 10 to the minus 4. Inverse seconds times the time, 865 seconds, plus natural log of the initial concentration, 0.0225. And if you, so notice the units, seconds cancel, and you carry out, let me see. So if you, okay, the book doesn't do it. Oh no, I guess it does. It goes minus 4.04. So natural log A of t. And if how you get rid of this, you take e to both sides. So e to the natural log of AT equals AT. Man. Oh, what the heck? Sorry about that. I guess my iPad wants me to upgrade my notability. So when you take the natural log of, when you take e to the natural log of anything, the original pops out, equals e to the minus 4.04 equals 0.0176 molar. So isn't this awesome? Isn't that so much easier? And this is great. I mean, this is how wonderful calculus is. I mean, I know you don't have to know calculus. You just have to know how to do it algebraically. Here's the algebra. It's just to use that equation. And remember, it's open note, open book. So you get all these equations. So all you got to do, and it's one equation, one unknown. And, you have to do a little bit of, kind of, I don't know, is exponentials and natural logs, is that kind of trigonometry. I guess it's our math 135. Where's it math 140? I don't know. So it's the 135, 140 level, and solving for those, and you can get the answer, and it's pretty easy. And it's, I mean, for chemistry, and I'd said that for things like nuclear decay, it may, like if you have like 10 atoms and you're looking at doing these kind of things with the integrated rate law, if you want to predict the concentration of something with 10 atoms and with exactly in time when each of those at a decay, these are not going to work very well. But if you have a big number of something like, I don't know, 6.02 times 10 to the 23rd, and you have and you have various time scales, yeah, it works very, very well. And for the most part, same thing with nuclear decay. Like if you have like a mole of uranium, or like, a planet that has a certain concentration of uranium in it, then yeah, it works very well for that. So, but we'll recap with this one. We have the first order, we're given a first order reaction. We want to know what the concentration is given an initial concentration and time. So we use the first order integrated rate law, and then we solve for the concentration. The only thing we have to do is raise the exponents. So we solve the natural log of the concentration, and then we get the minus 4.04, and then we put that, then we just take we exponent to both sides, and we get the concentration at that time after 865 seconds to be 0.0176 molar. We can even check. So it's a decomposition reaction. Here's our initial concentration. We expect it to go down. So it's a reactant. We expect the concentration reactant to go down. It in fact does go down. So, and it looks reasonable, you know. So if we got a number bigger, then we're like, oh, maybe I missed a negative sign somewhere on my calculator. But no, looks like passes the first, you know, sort of logic test there. And so as long as the math is there, it's probably correct. So questions with this though? All right, let's have you try it out. So we have cyclo, so pentane, that's cyclopentane to, let's see here, 1-methyl 2-propene. I guess, yeah, 1-methyl 2-propene. No, actually, I guess I have it backwards. It would be 2-methylpropene. So anyways, forms that molecule there. Cyclopropane turns into that alkane. Oh, no, sorry, it's just propene. What am I saying methyl for? Cyclopentane to propene. This reaction is first order, has the rate constant there at a given temperature. The initial concentration is given. What is the concentration after 235 minutes? And I did something sneaky here. What's the sneaky thing that I did? What's the sneaky thing? What are the units on the rate constant? Yep. Very good. Time here is minutes. That one's seconds. I always look up the new cases. There's 519 new cases in Hawaii, 54 or 53 on Maui. So that's actually pretty good. We're getting better. Oh no, it was 50 some yesterday and 100 the day before. And like whatever, like 3 weeks ago was 1,000. Yeah, we're doing a lot better. I'm seeing some people are still with their calculators. Is anybody getting stuck? Let me just, how many people link A, B, C, or D? Okay, so. Go ahead and spare you the suspense. Kiana, you have any, are you following or? Okay, got it. Okay, you just, okay. I've seen you guys use your calculators before, so I know you know you. But I mean, do you have any questions or? Okay. Oh yeah, this is a lot easier. Which is funny because the math is a lot more complex. So there's a saying they say with mathematics that the more advanced the math you go, the easier it gets. So, which I've mostly found to be true, but yeah, I think the hardest class, the hardest math class I've ever taken was Calc 2. So what is it here? Yeah, that was a horrible class. I've never understood Taylor series. Thank you. I know how to use it, but like, I mean, I understand what a Taylor series is. I just don't understand how, like, x squared, or something, times a derivative, plus the other thing equals like sine. I mean, I understand, like how you get the curvature and all that stuff, but I don't get it. But I mean, that's just like, I can use this, but I'll never quite understand it. So that's kind of the way I am with Taylor. Um, I I think it's probably the integration, like doing integration by parts and all that kind of stuff. And just it's like kind of like, I think 162, Chem 162 is easier than 161 because like Chem 161, you have like a bunch of new mental models, like, and when you come into Chem 161, it's like new day. Guess what? You learn something new that has nothing to do with the rest of the stuff you learned. But it's all related. You must know everything, It's kind of like that with Calc 2. Right? Because yeah, you have series and you have integrals and you have different integral rules, and then you like take coordinates and you rotate them and that kind of stuff. So well, good for you. Good for you. I'm glad. Awesome. It's just, I thought it was hard. And I thought linear algebra was really easy. Calc 3, that was a fun class, but I guess what my school did, we took what we call Calc 3 and Calc 4, we combined it into one class. So, but anyways, enough about calculus. This is chemistry. But yeah, but like I said, math gets easy as you go on. So first order integrated rate law. I'm sorry, second order. So second order integrated rate law. This is a solution here. Does anybody want me to prove it? If not, well, I can always derive it. Does anybody want to see the proof for it? Okay. So if you do the second order integrated rate law, you can similarly get a solution, and it's the inverse. And the reason being, so it's because it's squared, you have a squared, it's dx squared is, and the integral of dx squared is by the dx over x squared, it's with the power function, it's the minus of the inverse. And so you have the negative sign, so that way you don't have a negative here and you have a plus there. So that's the reason when you do the limits. So the inverse of the concentration sometime is equal to positive rate constant times the time plus the inverse of the initial concentration. It's the same thing, y equals mx plus b. And half-life, so some things you listed as the half-life. So also doubling time. So I told you banking interest is also first order kinetics. So half-life, and also in the other way, you look at it the other way, doubling time for investments. So if you ever, well, I'll tell that story in a little bit. We talked to some people, they train like realtors to do calculations really fast in their head. But anyways, so first order kinetics, natural log of initial concentration minus KT plus ln, and I'm sorry, time concentration, natural log of some concentration minus KT plus the initial, natural log of the initial. And so solving for half this concentration, you can put in the initial divided by 2, and you do the math, and you get the natural log of 2 is equal to, and time, not temperature. The time, the half-life time, the natural log of 2 is equal to the rate constant times the half-life, or you can say the half-life is the natural log of 2 divided by k, and the fraction for ln of 2, natural log of 2 is 0.693. So, well, I told you with investments, there's something called the rule of 72. So, and it really should be called the rule of 69, but some people might think that's a naughty thing to say. But the other thing is 69 is not a very useful number. It's 2 times, so it's, well, 69, it's 2 times, oh, sorry, 3 times 23. It's 3 times 23. So if you do the prime factorization of 69, it's 3 times 23. So so prime factorization, we look the breakdown of a number to the prime numbers. 72 is close to 69. 72 is divided by 2, 3, 4, close-ish to 5, because it's 70 is close to 5, and then 6. So, oh, and also 8, not quite 7. But anyways, that number is great for, and they train people to do that for investment purposes. And so if they tell you something like, oh, well, that also tells you the doubling time. So let's say that you invest $100,000 and your interest rate is 3%. So if you put it in a money market account, like, okay, well, this mutual fund gives you 3%. That means you will double your money in 72 divided by 3. So what is that? That's 24 years. So they tell you, like, okay, that means in 24 years, you're going to have $200,000. So at our 3% interest at our gain. And actually, what they're doing is they're doing first order kinetics here. It should actually be 23 years, because it's actually, the rule of 69, not the rule of 72. But I mean, like, they might come back, hey, guess what? We doubled your money in 1 year earlier. Aren't we that great? Kind of thing. But they train some of these people, the salespeople, to to pitch that way. So if you ever go to like realtor school, that's one of the things that they tell you. I'm not a realtor. I had a student that was a realtor, and he came to my office hours and tried to sell me properties, and then he was like spitting out these numbers. I'm like, where are you getting these numbers from? He's like, oh, okay. He taught me the rule of 72. I'm like, oh, that's not really the rule of 72, but sure. So anyways, that's a half-life. And of course, we very commonly associate half-lives with nuclear decay. So like the half-life of uranium 238 is about 4.5 billion years, for instance, or iodine 131, that's 8 days. So that means that like if there was a nuclear blast and a bunch of iodine 131 went in the atmosphere, in 8 days, half of it would go away. Another 8 days, it would be half would be a quarter, and so on. So here's a half-life, for instance. So if we can look at half-lives, and they work in set amounts of time for first order. And like I said, almost everything is first order. Of course, we do have chemical reactions that are not first order, which is the reason why us chemists, are so smart. Not really. I mean, I like to think we are smart, but we just have a very niche market on the kinetics that are not first order. So second order, the half-life actually depends on the initial concentration. So your half-life changes for second order. So they actually slow, it's very fast initially and it slows down. So, but for first order, it's very incremental. So, and these are even easier. So molecular iodine dissociates at 625 Kelvin with a first order reaction rate constant of 0.271 seconds. What's the half-life of this reaction? So half-life is just natural log of 2 over K. So ln of 2, what is K? Is 0.271 1 over seconds. And you put in your calculator. I'm going to cheat and look at the book. Too many lines. Is going to be 2.56 seconds. So that's pretty fast. 2.5 seconds. Of course, half-lives can be very fast and can also be very slow. So it depends on what you're looking at. So this one is usually pretty straightforward. Anybody have any questions with this one? Okay. So here is the summary. I didn't even talk about zero order. So zero order, the integrated rate law for zero order, it's minus KT plus the initial concentration, but zero order, I mean, it just, the rate is just constant. So, and the half-life is just A0 over initial concentration over twice the rate constant, because that's how long it takes to half go away. First order, we mentioned, so we have natural log of the concentration versus time. Oop, why is that moving? Stop. So natural log of the concentration versus time, and we get a straight line. I guess the graphical representations are important because, like I said, you can tell if you graph things out. If you graph out the concentration versus time and you see a straight line, you know it's zero order. If you graph out the natural log of concentration versus time and then it's a straight line, then you know it's first order. And if you take the inverse and notice versus time, and then it's a line, but it's a positive slope line instead of a negative slope line, you're like, aha, second order. And when you do this, I wish we could kind of like part of it we missed in the face-to-face. I have these things. They're the lab quests. They're digital input output devices that graphs it for you. When you, it's first order, but when you do zero order, it kind of, the data looks kind of like this. And when you try to do it second order, you do the inverse, the data kind of looks like this. So it's pretty obvious. And if you do it first order, it might, or you do it like the data looks something, it's not perfect, but you can see right away, like, okay, the natural log is pretty straight line-ish. The inverse is definitely a curve, and just the plain old concentrated versus time data, it's definitely not in zero order. So it's one of these things where it's pretty obvious. And if you want, you can go ahead and do like the curve fitting line, and then like the R squared value is like 0.98. And if you do like a linear here, it's going to be like the R squared is like 0.5. And then the closer you are to 1, for the R squared value, it's going to be error, and it tells you that it's right or not. Because so it's the error associated with the linear relationship as the R squared value. So, but it's, like I said, it's usually, at least in my mind, it's obvious. But then the half-life for first order is natural log of 2 over k. Second order, there's a different integrated rate law, and the half-life is it's inverse k times the inverse initial concentration. So, and so what with that is that your half-life is going to change. So the half-life for zero order doesn't change because it's just the rate constant. And well, if you do half-life, if you do 2 half-lives, it's all gone. So for zero order, your half-life, the amount of time it takes for half to go away, and then you do a second half-life, and then it's just basically it's gone. So I guess in a way your half-life does change, but I guess I think of it in a different way. It's like 2 half-lives and it's gone. Anyways, the first order, your half-life has a straight increment. You go from a half to a quarter to an eighth to a 16th, 32nd, and so on exponentially out. And second order, it starts out quick and then it kind of slows down as it goes away. So questions of this? I talk too fast. I usually go through that one lecture. I guess this is I have a lot of slides on this one. Yeah, okay, I can move on. All right. I can also tell more stories. So, all right. So I also talked to my chemistry and society class about this. This is like the non-majors chem. So the temperature affects a chemical reaction. So what affects chemical reactions? So the concentration is one, the temperature is another, and then a catalyst. So talk about chemical reactions. Let me break it down so it's really simple. I mean, I know I'm married, but let's say I'm trying to go and get a partner. And the way I get a partner is I'm going to go up to someone and say, hey, do you want to marry me? And if the person says no, I'm going to go somewhere else to someone else and ask that person, like, will you marry me? And then I'm going to keep on going till someone says yes, like, woohoo, I'm married now. And I've reacted and formed a couple. How can I make sure that I get married more quickly? So I can go to a place where there's more people, right? If there's more people, that means that when I get rejected, the next person I ask, I don't have to walk very far, right? So walking very far. And how else can I do it? What if instead of walking, what if I ran? So if I ran to the next person, someone said, no, I'm going to run to the next person. And that way, of course, I can talk to more people, increases the chances of me, getting married again, right? And of course, I know that I'm trying to use this kind of a ridiculous colloquial example, but the idea is something called collision theory. So when things react, I only have 2 hands, but they react by colliding. They have to collide. And so if there's more concentration, that more stuff per volume, that means there's more likely going to be the collision, thus more likely a chemical reaction. So higher concentration means higher rates. Same thing with temperature. So increasing temperature means increasing the speed, just like me running from person to person, you know, proposing my love, right? If I walk, it takes longer to meet someone. If I run, I can cover more ground. I have more collisions, more opportunities. Same thing with chemicals. When they move around, they can have more collisions. So that's, of course, part of the story. So temperature, and there's actually a range. So you can actually be too hot, hot temperature wise. So you actually get to a point, and this is not, you know, I'm not going to test you on this, but if you increase the temperature, the reaction slows down. So temperature of a chemical reaction only works under a certain range. So meaning like you can, if when you have reactions, and say you have these two molecules, you want to form this one, if they're moving around and then you get the right collision where they form, the problem is you can be so fast they just bounce off. So if it's a really, really high temperature, so like too slow and they never react, fast enough they can react, but if it's too fast, they bounce off. So that's actually, like I said, temperature is actually a range. And also when things react, it's you kind of wonder, like as I studied kinetics in grad school as part of my PhD research, especially in the gas phase. About 1 in every 10,000 collisions resulting in a chemical reaction is considered to be a very fast chemical reaction. So meaning like molecules, what usually happens, so if you want to form this molecule, usually what happens is molecules, they kind of bounce around and they kind of, and they fly apart. So when they're moving around, molecules are made of electrons, right? Well, on the outside, electron clouds. And when you have electron clouds come close to each other, what happens is they slow down. So they're moving fast and they come together. So, and they start to slow down. And if there's not enough energy, then their potential energy goes up. So they come up, the potential energy, their velocity is going on, potential energy goes up, and then they can just repel off. So you have to have a certain amount of energy to overcome this negative repulsion. And that energy is called the activation energy. The other thing is the collision. So if you have two spheres, if you have two hydrogen atoms and they react to form H2, every collision works. Doesn't matter what orientation. So if you have this molecule, these molecules forming this molecule, this collision won't work, this collision won't work, only this collision will work. That is part of the story. What also really happens is, so when molecules are flying around, they get together, they slow down, and they start to dance. And they actually can rearrange to something, and then they rearrange to what they want. You can get something called a transition state, where it comes here, and then it cuts kind of this kind of in-between state where it kind of fits. Then it can rearrange, or it could get the transition state and then it can fly apart. So it doesn't necessarily have to do it, but molecules actually dance. They kind of dance around each other for a long time. It's kind of like, have you ever seen two people fight before? Like, I mean, I don't mean like an MMA fight. I mean like on the playground or something like that. You know, it's kind of like, you know, like, you take my kickball? Like, yeah, I took a kickball. What do you do about it? Like, well, you know what I'm gonna do about it? I'm gonna fight you. And like, okay. And like, they're kind of like this, like people are just like dancing around each other, right? That's how molecules work. They kind of dance around each other. And of course, most fights, like at the playground, nothing happens, right? You know, all right, break it up, you know, or something. Or, I mean, it's absolutely nothing. Same thing with collisions. Like these things come together, like, then enough energy. oh, too much energy. Oh, let's dance for a bit. Oh, well, we got a transition state, and then we're gonna fall apart. It's only very, very infrequently that they actually do react. And so then we come to a catalyst. So what does a catalyst do? Catalyst does one of two things. It can lower the activation energy, or it can create, and it's usually and in this case, not necessarily or, but more and, has more effective collisions. So sorry if I'm being provocative with a fight, but let's say I really wanted to beat someone up, or so say I'm a mob boss and I'm like, I want to break that guy's nose. And so I go up to the person and like start my swagger, and the person would probably go like, okay, what's going on? And then we'd actually have a fist fight. Who knows if I'd break his nose? Maybe something else would happen. So, but what I could do is have one of my thugs go like, hey, see that guy? You two of my goons, I want you to grab that guy and put that person in a full Nelson so that person can't move. And then I'm going to go up and punch him in the face. So, right. And that's, molecule doesn't move, person doesn't move, single collision, 100% success. That's how enzymes work. So enzymes are biological catalysts. So they're proteins. And we talked before about enzymes. Enzymes are huge molecules. Proteins are huge molecules. There are some really simple proteins. Some are small. Insulin's pretty small. Even smaller are peptides like serotonin and melatonin. So, but most proteins that we have in our body are just absolutely huge. So if you have a protein like, or enzyme, which is a protein like amylase, the one that's the one in your saliva that digests sugar. So what happens is the sucrose sugar has this big clunky molecule. So it'd be like, so me with my holder, this is amylase, here is sugar. So it fits in right here. So it's this huge blob, and I have a receptor site, and the molecule fits in the receptor site ever so nicely. And then something happens where a piece comes off, or some reaction happens. So that's an example. That's an example of something like an enzyme. So big clunky molecule that holds another molecule in place, and then the chemical reaction happens, and it happens site specific 100% of the time. And that's important for biological things, because when we don't have room for randomness in our bodies, I mean, we have some, but when we have molecules, they're all very, very site specific. In fact, all of our sugars, for instance, are right-handed, meaning if you look at the groups, and you align the groups and you look at it, they all work counterclockwise. And our proteins are the opposite. Our proteins are, at least our amino acids, they all are lever rotatory. So if you look at the groups, and we put them in the order of importance, like a hydrogen is low important, and a carbon is slightly higher, and a nitrogen is slightly higher, it turns the other way around. It's lever rotatory. And and if we have if we have it mixed up, then the proteins don't have the right shape, and you can actually, if you have the wrong shape, you die, basically. I mean, so the shape is very, very important. So from that, all of our enzymes in our body are very, very site specific, and they also work very, very quickly. And I mean, like, so we burn sugar, right? We have the Krebs cycle, we burn glucose in our mitochondria, the powerhouse of the cell. Everyone always says the powerhouse of the cell, right? And this textbook, what's up? This is at least 50% or more of cellulose, which is almost all glucose. So I can burn this with oxygen, and it goes off very quickly. But like, if our bodies, we need to still get that energy, but we do it in a very controlled fashion. So how else can things? So I mentioned enzymes. The most effective catalysts are heterogeneous catalysts. So when you have different phases. So usually solid catalysts in liquid or gas. You have sites where typically the molecules break apart and they fall and then the chemistry happens on the surface. So I would say that's part of what I got my PhD in. Where'd my Apple Pencil go? Did I put it away? Aha! It was in my receptor site. So that's good. That's catalysts. So we'll talk about that in a little bit. So I told you about the rate constant. Rate constant, lowercase k, and this is also known as the Arrhenius equation. The rate constant, I told you, was a function of temperature. You have this pre-exponential term, and you have this exponential term. So E is exponent, and so the rate constant k is equal to a pre-exponential times E raised to the power of minus EA over RT. EA is the activation energy, and R is the gas law constant, and T is temperature. And you keep on wondering, where does R seems to be like, it's like, I mean, I have Avogadro's number that shows up a lot, but R is actually, it's Avogadro's number times what's called the Boltzmann's constant. So I mentioned that probability is what rules a lot of things. The Boltzmann constant deals with probability. It's where the mathematics of probability deals with large numbers. And so that's why you see the gas law constant and or the Boltzmann constant appear all the place, because it has to do with probability. So later on, if you study more chemistry, you can learn about the mathematics of big numbers and probability. And this pre-exponential factor can be described by, you can break it down to even further, say orientation, PZ, where you have orientation and the number of collisions. So, and for spherical molecules, or spherical collision, so like hydrogen atoms reacting to form hydrogen, that's a very, very high pre-exponential factor. So it's really easy to form H2 from hydrogen atoms, because, I mean, first of all, they want to react because they want the duet. The other thing is that it's a sphere. They don't even have to dance. And what does a dancing sphere look like? It's an electron cloud. I mean, it's not like it's not like a planet that spins. It's just a blob of electrons. There is no dance. I mean, they can dance, but the orientation from here is nothing different than the orientation there. Whereas if you have a molecule that has all sorts of dangly bits on it, this doesn't work versus this. So it depends. But spheres are great, especially atoms. So atoms are great in terms of effective collisions because they're all the same. Whereas if you have a clunky long molecule, orientation matters. And I even mentioned that they do dance. And although we don't see that as much with real data, we've done that with computer simulations. So it's cartoonish. Actually, I think so. A lot of banks. So the people that do, at least when I was in grad school, the people that I knew that were doing these calculations where they showed the simulations of molecules moving, the people that would snatch up those workers would either be like banks would love them because they could simulate things like markets. And the other thing was cartoonists. So I talked to somebody from Pixar that was, they were talking about how they do the cartooning in Pixar. I'm sure you know what Pixar is, right? And where when they do the cartooning, they do it with, they start with Newtonian physics. So let's say you're trying to move your arm. So the way that they would try and, they would model someone moving an arm. they would do it with mathematics. So you have the arm moving, but it's moving at a rate, but then I can't do it. I'm not double jointed, right? But if like the elbow would kind of go like this, it would be like a circle. Like the elbow would keep on going in a circle, but of course that doesn't look natural. So then they would like this, like, but I mean, no one, moves arms like this, because when you move, you're kind of fast and you slow down. So they're talking about like how they would start with like physical relationships and then they would tweak them. But in molecules though, you don't have a joint, right, where you have to worry about, it snapping back to hurt. So when molecules are moving, they move. It would be more like a weird sort of Pixar cartoon, although Pixar is looking more and more real. So, but so that's where we get the molecules dancing. So it's not real data. It's kind of what we infer. But this is Arrhenius back in the 19th century, and we didn't have computer simulation, so he kind of just went around and said, okay, pre-exponential, this is probably what it means. Okay, and before mentioned, I talked about the transition state. So looking at this graph here, you have the y-axis. The y-axis is potential energy. It says energy, it's potential energy. X-axis is the reaction progress. It's usually an internuclear distance. So something like the distance between a hydrogen atom and an oxygen atom. So if you start off here on the left, so reaction progress, very long distance, you have hydrogen and you have oxygen, and the hydrogen and the oxygen distance is very far apart. So, and then as it reacts, what's happening is the hydrogen, so the oxygen and the hydrogen, they're coming close together, and then they break apart and form water. So I can't mime that because I can't tear these apart. Well, I guess I could, but then I wouldn't be able to put them back together. So a couple features. So as the reaction is progressing, so right, these are made of electron clouds, or at least on the outside. They're moving fast, they come together, they start to slow down. And then not only they slow down, but the potential energy goes up. As they slow down, potential energy goes up. And if there's not enough potential, if there's not enough velocity, then no reaction. If there is enough velocity that they can collide, then they can form a transition state, and then they can react. And in transition state, it's very frequently a saddle point. It's not always, but did you guys study saddle points yet in calculus? No, you haven't. Okay. So it's like a local minimum on a potential energy surface. So it's because things tend to kind of collect in there and fall in there, the local minima. So, and that's it's funny. I just had a connection. It's not an exact connection, but are you guys familiar with the James Webb Space Telescope? Okay. What's that? It's there, yeah. It's up. It's at a point called the Lagrange point. It's the L2. It's a stable gravitational point between the sun and the earth. So if you have three bodies, it's a very stable. It's the gravity of the earth and the sun kind of cancel out at these points, and they're very stable for orbits and whatnot. So and because of it, there's a lot of junk there, usually like asteroids and stuff. So there's a lot of junk around where the James Webb Space Telescope, JWST, is hanging around. It's kind of a very stable point. Transition states are kind of like that. They're very stable points. So and it's stable so that that the chemical reaction is drawn towards it, so that as things are reacting, they're drawn towards that. And this is another kind of advanced topic, not tested on, but we're looking for life right now. So that's one of our main aims. And one of the things that JWST, I think that they're going to try and go for, they're going to look for molecular oxygen. And if we find a large amount of molecular oxygen on an exoplanet, we're going to be like, haha, we found life. So I mean large amount. So Mercury, the planet, has an atmosphere that's 35% oxygen, but it's a very thin atmosphere. Nothing can grow on Mercury, right? Or nothing can survive. As far as we know, life as we know it can't survive on Mercury. The Earth, we have a 20% oxygen atmosphere. That comes directly from life. So mostly algae, right? So the oxygen in our atmosphere is mostly from algae here on Earth. So it's not a natural, well, it's natural life, but it's not a geological process. So if we find oxygen somewhere in a large amount, we're like, haha, found life. But for life to form, and we keep on looking for all these molecules, and I mentioned that for our bodies, we have to have things aligned in a very specific fashion. If you go on and study organic chemistry, there's a type of reaction called an elimination reaction. That's when carbon forms double or triple bonds. So carbon forming double and triple bonds can only happen in a liquid environment. And the reason is because of the transition states. So this, and we have this transition, the way we usually indicate that is just like this double cross kind of thing. So the transition state, it needs to be stabilized by the solvent. So you have to have a liquid around it to do it. Otherwise, so carbon in space, if you have carbon reacting in space, it's going to be you'll hit some, but you will not have a very appreciable amount of any sort of double or triple bonds. And that's important for life because we do need those double and triple bonds for the chemistry. So things, and we need that for ourselves. I mean, when we talk about healthy fats, we talk about polyunsaturated fats. Unsaturated means double and triple bonds. So if we don't get them, we die, right? So if we for life as we know it, we need that. We need the liquid phase. So, but okay. So, but the transition state, this is like the in-between state. You can colloquially, I know I'm kind of talking about chemistry and society right now. You can think of it kind of like engagement. So like you can, and you can have multiple transition states as well. So kind of like you can have like a dating relationship and you have a married relationship, and there's this transition state in between. It's your engagement where you're planning out your marriage. Same thing with the molecules. So they're flirting here, and now they're kind of like, well, let's set up our future, and haha, here's our future. So that's the progression. You can see the transition state kind of like that. And some other things. Look at this graph. You have the potential energy of the reactants here and the potential energy of the products here. The difference between this potential energy, this is the heat of the reaction. That's the enthalpy. So the heat of the reaction is the overall look at the thermodynamics there. So that's the other thing that makes this chapter so difficult, is that we have to look in between the endpoints. We're seeing what's going on in between the endpoints with the activation energy. So, and so also a temperature, and I mentioned temperature affects chemical reactions. So if you look at a couple of things, so here you have in blue, you have one temperature, and you have red, the longer distribution for a higher temperature. And you can see for the red line, the area underneath the curve, at least for, if you say this amount of energy, that's the activation energy, then you can see that there's a greater fraction of the molecules, the reactants that have enough energy to react. So because of that, it's going to react faster, generally speaking. And you can also have really cold things. And even at really cold temperatures, you still can have a little bit that has the amount of energy to react. So with that, has anyone ever seen really old paper before? I mean, like really, like a Gutenberg Bible like, or something like that, or even just even a book that's 200 years old. Has anyone ever seen paper that's that? No, okay. Okay, yeah. What, Kiana, what does it look like? What color would you call it versus normal paper? Musty, yellow, yes. And so why is it doing that though? It's because it's burning. It looks like it's burning. It's burning very, very slowly because at this really low temperature, we have a little bit, there's a little bit of energy that can break down. I guess it wouldn't necessarily be paper. It'd probably be like animal skin or whatever they're called, parchment or vellum. I guess vellum. This parchment is something different. So it's it's reacting ever so slowly. And so for one of the things though, we if you ever go to the archives in Washington, D.C., we have like the Declaration of Independence and our Constitution, the original copies, one of the original copies of both, and they keep it in helium. So they have it in helium, and if you ever go in the archives, that building is cold. So which is great because I always went to Washington, D.C. in the summertime with my family. We always have a family reunion around the 4th of July, and I can tell you DC is hot in July. And it was always nice to go to the archives because it's so hot outside. You go inside and it's nice and cold. So they keep the building cold, and they also they keep the Constitution and the Declaration of Independence. They keep that under helium, so it's very unreactive. So, and they tell you not to take pictures of it either, or at least not with your flash, because the photos, the photons can damage the ink, I guess. So, yeah, that's a cool building if you ever get a chance to go to the archives. They keep a lot of interesting things. Like I remember, and they rotate the exhibits. They had one time I saw they had the canceled check that Russia cashed for when we bought Alaska for 15 million. You know that we bought Alaska from Russia for $15 million. So they had the canceled check for that. They had an invitation for the president at the time for Napoleon Bonaparte for his wedding. Let's see here, what else was there? Oh, they also have the Magna Carta. I think I've seen that more than once. They have a copy of the Magna Carta, which is even older than the Constitution. So anyways, so if you were to take this textbook, I know you guys do electronic, but if you take this textbook, I bet you with like a welding torch or like even a propane plumbing torch, I could probably burn this thing in a matter of minutes, right? So, or I could keep it at 25 degrees Celsius. And so what a torch has temperature range of around, so it's about 1500 Fahrenheit. So what is that in Celsius? That's going to be 700-ish Celsius. So a couple minutes at 700 Celsius or 25 degrees Celsius, it'd probably take like, I don't know, 1,000 years, I'm guessing, right? So you can have chemical reactions can happen very slowly in some ranges and very quickly in others. And much of that has to do with temperature. And so the activation energy is a big deal. So the activation energy was what keeps things from reacting. Or, but I think I'm about out of time. Okay, yeah, I'm about out of time. And I guess this is where we'll pick up on Monday, Super Bowl Monday. So are you guys gonna watch the Super Bowl? I'm excited. I was born in Cincinnati, so yeah, question, Dennis. Yeah. Yes, it will. Yes, if you, or actually ash can go away too. That's in a way, so it also depends on what's in it. So if by ash you mean carbon, yes, it can turn into black carbon first, but ash is also especially fly ash, like the stuff that floats up, that's also typically calcium and magnesium silicates. So yes, if there's any calcium, magnesium, and silicon, if there's calcium, magnesium, and silicon in this, then yes, it will eventually turn into the fly ash as well. But I mean, it depends on what you mean by ash, because ash has a lot of other things. It can also have potassium in it, for instance, because it's plant. You can have potassium carbonate. It's another form of like what's in ash. So it's a complicated question, kind of has a complicated answer. It just depends what you mean by ash, and there's different types of ash. So like the pot ash, potassium carbonate, they will turn into that as well. Yes. And the fly ash, calcium, magnesium silicates, if there is enough calcium and magnesium and silicon in this, then yes, it'll turn into that as well.